Welcome to the UGC lecture series. This is the EPG Pathashala lecture series on the subject of computer science, and we are talking about the paper machine learning. In this module, we are going to discuss cluster analysis and cluster validity. In the previous two modules, we had discussed about clustering in general and two basic methods of clustering called hierarchical clustering, in which we discussed agglomerative clustering in detail, and the partitional clustering, in which we discussed k-means clustering in detail. Now, these are the people responsible for the development of this module, and these are the learning objectives of this module. So, we are going to look at how to understand what we mean by cluster validity and how do we carry out the cluster validation process. Then we are going to look at the different measures of cluster validity, very important, because clustering, as I told you, is a very important component of any machine learning, data mining, big data analytics problem, and trying to find out how good your cluster is a very important aspect of the clustering process. And there are different types of measures. So, we are going to understand external, internal and statistical framework for determining cluster validity. So, the keywords here are cluster validity and external and internal measures. We look at what they are in detail as we go along. So, first, before we start off, we have to define what we mean by cluster validity. Now, this is a quotation by Janes and Dubes, who says that the validation of clustering structures is the most difficult and frustrating part of cluster analysis. Now, this term cluster analysis has been used long time previously for other types of processing, including image analysis. So, the term cluster analysis is used. So, he tells that it's the validation is one of the most difficult part of any cluster analysis. Without a strong effort in this direction, that is in the cluster validation direction, cluster analysis will remain a black art, accessible only to those who truly believe this and who have the experience and great courage. It cannot find uniformly acceptable application. That is what he tries to say. So, you have to prove to others that your clustering process provides valid clusters. So, what is this cluster validity? For cluster analysis, the question is how to evaluate the goodness of the clusters that you have formed, resulting clusters of any algorithm. So, but clusters are in the eye of the beholder. Okay, that is what they say theoretically, but actually speaking, clusters is based on the feature that you choose to cluster it on. Okay. So, validation, why do you need validation? It is needed to compare two clustering algorithms, and it is also needed to solve the number of clusters. If you find that your cluster validity is not good, that means something wrong with the number of clusters. It is also used to compare two sets of clusters, and it is also used to compare just two clusters, and it is also used sometimes to ensure that you have not found patterns in noise, because some of the data points may be noise. So, this is an example, a small example of what we mean by this. So, you have oranges and apples. So, the first cluster that has been formed, you have cluster set that has been formed. You have two types, clusters, cluster 1 and cluster 2. On the top cluster, you have precision, that means all the 5 precision is good, 5 by 5. So, it is 100%, 5 oranges you have found 5 oranges, but recall is bad because you have 5 out of 7. Okay. So, 71% recall. Here the precision is 3 by 5, 60%, but all the cluster points are actual correct cluster points. So, you have 100%. So, this is precision recall. We will go into precision recall in detail later on, but just to give you a feel of what you mean by precision and recall. Now, what is good clustering? So, in internal criterion, a good clustering will produce high quality clusters, that is the meaning obviously, in which intra-class similarity is high and inter-class similarity is low. So, this is how we decided and defined our clustering algorithm itself. So, a good clustering will produce this. The measured quality of clustering depends on both the document representation, if it is a document clustering, and the similarity measure use. Finally, your clustering depends on that. So, external criterion. So, here what it means is you are not looking at anything outside, you are just checking good clustering by checking that the distance between the points inside a cluster is low, and the distance between the similarity or distance between intra-class similarity is high and inter-class similarity is low. and if you tell in terms of distance, intra-class distance is low and inter-class distance is high. So, it depends only on that, but if you take an external criterion, the quality of a clustering is also measured by its ability to discover some of the hidden patterns or latent classes. We will come into the detail about this as we go along. For doing this, whether we have got that whatever we wanted to get, you have to have a gold standard. So, if you have gold standard data, you can do external criterion. So, in this module on cluster validation, we are going to see if you have external gold standard data, how do you do it, and without it, how you do it. So, let us look at some aspects of cluster validation. Comparing the clustering results to ground truth, that is externally known results, this is for that you use an external index. Evaluating the quality of clusters without reference to any external information, that is called use only the data, and that is called as internal index or external measure and internal measure. And the next is the determining the reliability of the clusters. Okay. To what confidence levels these clusters are not formed by chance. So, you have three aspects: comparing the clustering results to the truth values, ground values or the gold standard, which is called as external index, or evaluating the quality of the clusters without reference to any external information, use only the data, this is called as internal index. And another point aspect is determining the reliability of clusters, that means how reliable is it, what confidence can you give that the clusters are not formed due to by chance or by randomly. So, this is based on what is called a statistical framework. So, you have external index, internal index and statistical framework. Now, let us look at the process of cluster validation. How do you do the cluster validation? So, determining the clustering tendency of a set of data, that is distinguishing non-random structure that actually exists in the data. Okay. If it is one cluster, that is the clustering tendency, it is only for one cluster. Comparing the results of cluster analysis to externally known results, that is already given some class labels you are comparing. Evaluating how well the results of the cluster analysis fits the data without reference to external information, that is the internal, use only the data, we have already spoken about this. Comparing the results of two different sets of cluster analysis to determine which is better, that is another method. Determining the correct number of clusters, that is another method. For steps 2, 3, 4, we can further distinguish whether we want to evaluate the entire cluster or just individual clusters. So, there are two methods, that is cluster itself or the clustering itself. So, that is what it is called. So, cluster validation refers to procedures that evaluate the results of clustering using a quantitative and objective fashion, in a quantitative and objective fashion. So, how to be quantitative? You have to employ the measures. How to be objective? You have to validate the measures. So, this is a method of you are given the input data set and you have the clustering algorithm and you have the partitions and then you have a validity index. You find the different number of clusters, you would keep doing this algorithm and the validity check and find out where M is the number of clusters. So, one way of validation is you keep changing the number of clusters and try to do this. So, this is one method of doing it. So, that is the partition or the code book C, it is also called terminology. Now, let us look at the measures of cluster validity. The first measure we will look at is the external measure, the external index. So, you have to validate it with the ground truth. Okay. So, or you can compare how two clusters are, how similar they are. So, that is two things that you can do with external index. In the case of internal index, validate without external information. Okay, just take a cluster and validate it. You can validate it with different number of clusters or you can solve the number of clusters, how many clusters should it be. So, all these three comes under internal index. Now, comparing to ground truth at the external index, the notation that we use is the n is the number of objects or data points in the data set. P is the number of P1 to Pm is the set of ground truth clusters, that is the remember it is an external source. So, what you are talking about here is the gold standard clusters. And C1 to Cn is a set of clusters reported by the clustering algorithm. Okay. And the incident matrix we will define is n into n, both rows and column correspond to objects, and Pij is equal to 1 if and only if object I and object A belong to the same ground truth cluster in Pi and Pij otherwise. What it means is I have ground truth clusters and I have this R clusters formed by the clustering algorithm, and we have the objects. Now, if this object falls in both in the same cluster, you put a 1. If it falls in different clusters, put 0. So, this is the incidence matrix. Now, if Cij is equal to 1, if Oi and Oj belong to the same cluster, and if it is 0, otherwise. Okay. So, cluster found in random data, if you have random points, DB scan, complete link, a lot of data which have random points. So, how do you cluster it? So, if you see the DB scan, it is clustered like this. Complete link method using hierarchical clustering, it has clustered it like this. DB scan is a method, is a algorithm available, and K means clusters it like this. So, any pair of data objects Oi and Oj fall into one of the following categories. One is SS, that is both the objects fall in the same cluster and they fall in the same ground truth also. Remember, Pij stands for the ground truth. DD means agree, both do not fall in the same clusters. SD means disagree. In R clustering algorithm, it falls in the same cluster, but in the ground truth it does not. And the other one DS, in which in ours it forms in different clusters, but in the original ground truth, not original ground truth, it does not fall. So, I mean Cij does not fall in the same cluster, here it falls. So, this is again disagree. So, these are the 4 sets we have in the incidence matrix. Okay. So, what we use as external index, one of the indexes is called the RAND index. So, the RAND index is given like this: agree divided by agree plus disagree. So, agree is SS plus DD divided by SS plus DD plus SD plus DS. So, all this together will give you the RAND index. So, where in general it gives a conceptual view of where all agreement happens and where all out of the total number of agreements and disagreements, how many agrees, what is the percentage, and this may be dominated by DD, that is it does not fall, both are given 0 value. So, it may be dominated by that. So, another method is the Jaccard coefficient. Jaccard coefficient also uses the same categories that we have defined here. It is divided as SS followed by SS plus SD plus DS. So, that means we have just eliminated the DD, where the object we are not bothered about whether it falls in the same cluster or not, we are, I mean it's 0. So, SS they agree divided by agree, agree and disagree. So, these are the 3 methods, only the DS we consider. This is the Jaccard coefficient. Now, let us look at what we mean by a confusion matrix. We have already looked at confusion matrix in binary attributes. So, let us look at what we mean here. Let n be the number of points, data points, mi be the points in cluster I. So, mj will be the points in cluster j, cj is the points in class j, okay. Class j, class means according to the ground truth. Nij is the points in cluster I coming from class j, okay. And Pij is Nij divided by Mi, it's the probability of the element from class I to be assigned to class j, that is it should not be assigned to class j, but this is it has been assigned to class j, that is the probability. So, let us look at this confusion matrix. You have the 3 clusters, cluster 1, cluster 2, cluster 3, and you have the 3 classes C1, C2 and C3, and cluster 1 class 1 Nij is a cluster I coming from class j. So, cluster, for example, just let us take Ni2, it means that the points in cluster I are coming from actually cluster j or 2, cluster 1 is coming from class 2. So, that is the meaning, and the meaning of M1, M2, M3 is the points in clusters. So, that is the total confusion matrix. And then we have another matrix which again consists of C1, C2, C3, the 3 clusters, and the 3 classes M and the 3 clusters, and cluster 1, cluster 2, cluster 3. Here, for example, if you take P21, it means the probability of the element from cluster 2 to be actually assigned to class j, that is class 1. So, that is the probability. So, this way we have defined the confusion matrix. Based on this, we have what are called as purity based measures. So, this is given to us. So, entropy is the first measure we will be talking about. This entropy we define in a lot of scenarios. we do use in information theory. Here we are defining it for cluster validity. So, entropy, first we will try to find out the entropy of a cluster I, which is given as EI is equal to minus j is equal to 1 to L Pij log Pij, highest when uniform, 0 when it is a single class. The same entropy can be given for a clustering, where E is equal to I is equal to 1 to k mi by n. Mi, remember, is the cluster, okay, by n, the number of data points EI. EI is already calculated. So, this is entropy. Purity of a cluster is Pi is equal to the maximum Pij, and of a clustering P of C, that is the complete clustering, is I is equal to k 1 to k mi by n Pi. Pi is calculated as before. So, this is the purity based measure of entropy and purity of a cluster. Okay. The entropy measure is the same as the normal definition of entropy, but Pij corresponds to, as we have already defined, Pij corresponds to the probability of I being allocated j. Now, with the same measures or the matrix, we can define precision and recall. Now, how do you define precision? Remember, we started off by defining precision just in an ad hoc manner. So, precision of cluster I with respect to class j is precision Ij is equal to Pij, and recall is of class cluster I with respect to class j is recall of Ij is Nij divided by Cj. Okay, Nij divided by Cj. Remember what Nij? Nij is the number of points that have from in cluster I, that is come from cluster class j. So, F measures the same way that you define precision recall F measure group, 2 into precision of Ij into this recall of Ij divided by precision of Ij plus recall of Ij. This is the harmonic mean of precision and recall. So, this is for a cluster. Okay, we are not talking about clustering. Please remember what is the difference between cluster and clustering. Cluster means about a cluster, clustering means of all the clusters together, overall angle. So, the same precision and recall you can do for clusters and clusterings. So, here we have assigned to cluster I the class Ki such that Ki is equal to the argument max j of Nij, and precision of cluster I is equal to already given, of a clustering is equal to, the same way you have to do it for all the clusters and the data points, you have to find the precision. Similarly, recall, we already know recall of I is equal to Nki by Cki. So, the recall of the whole clustering, that is what is C, is you have to do it for each and every cluster, and F measures the similar way. Now, let us look at good and bad clustering. Now, let us take a class. Now, look at the number of points that we have here. Now, you have the purity now you have to calculate the purity, precision and recall. Here you have the values given. So, this is a good clustering. A bad clustering will give you very low values of precision, purity and recall. The calculation has been done based on, for each of the clusters has been, this is an overall clustering, okay. This is not for a cluster, overall clustering. So, we have used the purity, precision and recall definitions that we discussed before for overall clustering to find out this, and you find that for the same data points, depending upon how you cluster, this is the values that you get. If you look at these values, you will see that depending upon the class 3 and cluster 1 should both, I mean whichever is giving maximum values towards one cluster or one class is the one that is giving a better clustering, the differentiation. Now, let us look at internal measure. Till now what we looked at was external measure. So, that was the classes available for the gold standard data, classes were available and we had a set of clusters, we were looking at them. Now, we look at internal measure. This is used to measure the goodness of clustering without respect to external information, because having this gold set is not very common, especially when clustering, when we are talking about unlabeled data set. So, there are two aspects. Cohesion measures how closely the related the objects in a cluster are, and separation, this measures how distinct or well separated the cluster is from other clusters. So, these are the two aspects, and this is cohesion and this is separation. So, for doing this we measure internal measure sum of square errors. So, cluster cohesion is the homogeneity is measured by within cluster sum of squares. So, between the data points in a cluster, how do you calculate the sum of squares? and this is given as WSS within cluster sum of squares is considering one single cluster and xi minus mi the whole square. This is exactly the objective function of k means. Okay. So, this is the within cluster sum of squares, and cluster separation is measured by between cluster sum of squares BSS is equal to I the cluster and m minus mi, where Ci is the size of cluster I and m is the centroid of the whole data set. Whole data set you take a centroid, and then you compare, I mean you take this cluster, each centroid, and find the difference. The original one, the data point and the centroid of that particular data set. So, that is cluster cohesion or homogeneity and cluster separation. So, WSS and BSS. So, this WSS plus BSS will be a constant. A larger number of clusters will result in smaller WSS, okay, and because the within cluster will not be good. Now, let us take an example. Here I have M1, M2. So, k is equal to 1. For k is equal to 1, that is M1, 1 minus 3 the whole square plus 2 minus 3 the whole square plus 4 minus 3 the whole square plus 5 minus 3 the whole square is equal to 10, and BSS is equal to, the average is 3. So, 4 into 3 minus 3 the whole square is 0. So, total is 10. Now, if you take k is equal to 2, you will have 1 minus, if you take 2, 1 minus 1.5 the whole square, we are taking 1.5 as the mean, 2 minus 1.5, 4 minus 4.5 and so on. So, I get 1 and BSS is equal to 9. So, I get total of 10 and so on. So, k is equal to 4, if I take, I get 10. So, this is how you measure the WSS and BSS. Now, SSS curve is for a more complicated data set, could be of any type, any direction, and another internal measure that we are going to discuss is what is called as Silhouette coefficient, and this is used to measure cohesion A of x. Is the average distance of x to all other vectors in the same cluster. So, between the data points they are trying to find, not between the data points and the cluster, and separation B of x is the average distance of x to the vectors of other clusters. Find the minimum among the clusters. So, the Silhouette coefficient S of x is equal to B of x minus A of x divided by the maximum of B of x, A of x and B of x. So, if S of x is minus 1 plus 1, minus 1 means bad, 0 means indifferent, and it is 1 means it is good. So, this is the values. So, here the difference is we are finding out between the data point and all the other vectors in the same cluster instead of between the center. So, Silhouette coefficient of complete clustering, as it is called, is defined as SC is equal to 1 by n, I is equal to 1 to n of S of x. S of x is found in that way for each and every cluster. Now, correlation with distance matrix. Suppose you have two matrices which is called as proximity matrix and distance matrix, where Di is the similarity between object Oi and Oj, I mean Dij is similarity between object Oi and Oj, and then you want to compute the correlation between the two matrices. Okay. So, only n into n minus 1 by 2 entries needs to be calculated. High correlation between the two means good clustering. Okay. So, given the distance matrix D is equal to D11, D12 to D1n, and the incidence matrix where you have the actual clustering, the correlation R between D and C is given by this, where this is equal to Dij minus D mean, that is the, and Cij minus C mean, and this is the usual calculation that we do, but we are taking two centers of the two distance matrices calculated. It is not a good measure for density or contiguity based clusters, only for some clusters you can use this method. And correlation of incidence and proximity matrices for k-means clustering of the following two data sets, you will see that the correlation for this data set is like this, high, and for the other data set it is low because the cohesion is less. You can use similarity matrix also for cluster validation. You order the similarity matrix with respect to the cluster labels and then you inspect it visually. So, this is another method which is done. This is the points and the how you inspect it visually. So, you get it for different clusters in a random data, the clusters will not be so, for example, DB scan will not be very crisp. So, this is another method where you will find that the colors are spread throughout. So, next we will talk about the statistical framework for sum of square error. So, compare SSE of 0.005 against 3 clusters in random data. So, SSE histogram of 500 sets of random data points of size 100 distributed over the range of this, and so this is an example. So, correlates of incidence and distance matrix of the k-means of the following 2 data sets. So, depending on the correlation we can find out how good our clustering is. So, we have something called an empirical p-value. So, if you have a measurement versus for example, the SSE value, and we have n measurements on random variables, the empirical p-value is a fraction of measurements in the random data that have value lesser or equal to the value v, or greater than or equal to, if you want to maximize it. That is, the value in the random set is at least equal to the or as good as the value in the real data. We usually require that p-value must be less than or equal to 0.05, because otherwise you are only catering to random. Hard question, what is the right notion of a random data set? So, you have to create the random data set. So, that is where we talk about hypergeometric distribution. Given the total number of genes in the data set associated with term T is m, if randomly we draw n genes from the data set, n, what is the probability that m of the selected n genes will be associated with T? So, randomly. So, that is given by this distribution which is there, and this can be used also to find out the clustering goodness. Because what we are trying to do here is we are trying to say that the clustering algorithm is better than a random sampling. That is what we are trying to say. So, based on hypergeometric distribution, the probability of having m genes of U associated to T in n can be calculated by summing up the probabilities of random list of n genes associated to T. So, the p-value of over representation is given as follows. So, you should have a p-value less than or equal to 0.05. With that, we will talk about what we have discussed in this class. We explain the different aspects of cluster validity and cluster validation process, and we discuss the roles of different measures in determining cluster validity, and explain the external, internal and statistical framework that was used for determining cluster validity. So, basically what we covered in this particular very important module was cluster validity, and we spoke about cluster validity in 3 terms. One is in terms of having an available goal set and comparing it, and the second was by having no gold standard, we used only internal measures to compare it, and the third one we used a statistical framework to ensure that randomly allocating clusters, and the clustering algorithm, this clustering algorithm does remarkably or markedly better than the other one. And in external measures and internal measures, basically we were looking at in external measures especially we were looking at purity with respect to the given class labels, because there are external data was available, and we also looked at precision and recall. That is possible only because gold standard is available. But if you do not have gold standard, which is quite normal in clustering, then we go for internal measures. In internal measures we look at basically oriented, whatever the measure is, cohesion and separatedness. Between that is between the points in a cluster, they should be cohesive, and between points in another cluster they should be separate. In one method basically we used compare the data points with the cluster center and the cluster center of other clusters, while for another method we compare the data point with all the other data points in the cluster and with all the other data points of other clusters. So, this was cluster validity. As you can see, cluster validity did require to do some amount of processing before you arrive at how good your clustering is. Thank you.